All right. Now I got that going. This is my real squiggly, which makes more sense. Okay. So, quick review for what we talked about in our last chapter. What was our last chapter completely focused around?
Congruence.
Congruency. What did it mean intuitively for two segments to be congruent?
The same length.
The same length. That was our intuition guiding us. Of course, what does congruence actually mean? What's the definition of two things being congruent? There isn't any. Bad question. Congruency is now one of our undefined terms. So we introduced a new undefined term, congruency. And if it's undefined, that means it's meaningless. Congruence doesn't mean anything, right? No, it means something. How do we give undefined terms meanings?
Through theorems.
Through the postulates. The axioms are the postulates. And so we had these postulates telling us the behavior of congruence, the congruence relation. So first off, it's a relation. It's a two-term predicate. You give it two terms and it spits out true or false. Right? Two segments. Are these two segments congruent? True or false? Yes or no? Right? So it's a two-term predicate. It's a relation. And here's the rules that follows. So postulate group 3, we had number 1. Number 1 said, if I gave you some segment AB, and I gave you a point A prime on some line L prime, then there exists a unique point on either side of A prime, call it B prime, such that the resulting segment is congruent to this segment. So there's one and only one point over here, such that this segment is congruent to this segment, and there's one and only one point over here, such that this segment is congruent to this segment. Make sense? Our second postulate told us that congruence is an equivalence relation. It's an equivalence relation. It's reflexive, symmetric, and transitive. What does that mean? That means every segment is congruent to itself, reflexive. That means if segment A is congruent to segment B, then segment B is congruent to segment A. That's symmetric. And then if A is congruent to B is congruent to C, then A is congruent to C. That's transitive. So congruence was an equivalence relation. Those show up a lot in math. You'll get used to just referring to things with those three properties as being a congruence, an equivalence relation. Okay. The third postulate. What did the third postulate say? My picture's not doing enough to remind me. Equals add to equals or equals and equals subtracted from equals or equals. That's what it says. So if AB is congruent to A prime B prime, and BC is congruent to B prime C prime, then AC is congruent to A prime C prime. That was one. Equals added to equals are equals is the mnemonic to remember. And then if I know AC is congruent to A prime C prime, and I know that AB is congruent to A prime B prime, then I know that this segment is congruent to this segment. So I start out with two equal pieces. If I take off an equal portion from each of them, the result is equal. Equals add to equals are equal, and equals subtracted from equal are equal. That's the mnemonic for remembering that one. Okay, and that was it for our new postulates from that chapter, right? Okay, now the definition that was a tricky definition from the chapter was less than and greater than. It's going to be very hard for you to think about these in terms of exactly what they give you. So if I know that segment AB is less than segment A prime B prime, what does that exactly mean? So AB is less than A prime B prime. That meant that there is some point B double prime, such that AB is congruent to A prime B double prime. So I can find a point over here, such that AB is congruent to A prime B double prime. And B double prime will be between A prime and B prime. So find the point that makes it congruent, and it's going to be between these two if AB is less than A prime B prime. Good? Now, if AB is greater than A prime B prime, what does that mean? So AB is greater than A prime B prime. We can still find that point B double prime that makes these two segments congruent, but this time that point B double prime will be beyond B prime. And so B prime will be between A prime and B double prime. So what does it mean for AB to be greater than A prime B prime? It means AB is congruent to A prime B double prime, and B double prime goes beyond B prime. I don't know if you can see that prime very well. That's prime. A prime, B prime, B double prime. Make sense? Okay, so that was our quick recap for that. Okay, today, this chapter, in terms of intuition, it's a pretty straightforward chapter. There's three big ideas in this chapter that we're after. This is probably the easiest chapter we're going to cover in the book, in terms of your homework. It's going to be a bit weird what I do up here, seem a bit hand-wavy, and that's just the nature of the chapter. Okay, so the first big idea is length. we're going to be talking about the length of something now. Suppose I asked you the length of this room. How long is this room, roughly?
20 feet.
20 feet, maybe? How would we determine that?
Lay down a ruler 20 times.
Yeah, we take a ruler and we literally lay it out one at a time, one piece at a time. And however many rulers we lay out, that is the length of this classroom, right?
Yeah.
So what is a length? A length is a number, a real number, a number, together with some unit. Suppose I said this length is, or this classroom is 17.
17 what?
17 what? I saw that building, it's 13 over there. 13 what? 13 meters? How tall is it? So you need a number together with units. Make sense? Okay, so that's going to be the first big idea. What is length? It's some number together with units. That's a length. Okay, the second big idea is going to be this. Pick a unit, any unit you want. Meters, yards, feet, miles. Any unit you use, you can measure this classroom in terms of that unit. You can give it to me in feet, you can give it to me in meters, you can give it to me in miles, you can give it to me in kilometers, you can give it to me in light years. Right? Doesn't matter what unit you use, it changes the number that comes out, but the point is you can use any units. So that's the second big idea. Pick a unit. Every segment has a length in terms of that unit. That's going to be our second big idea. What's our third big idea going to be? This time, pick a length. 127 miles. Pick a length, any length. There exists a segment with that length. Pick any length you want, I can create a segment that long.
Yeah.
Those are going to be the three big ideas of this chapter. Make sense? Pretty straightforward, right? Okay. So, before we get too much into the length of things now, let's actually think a little bit about numbers and the types of numbers that we talk about, and take you through a quick evolution of how you've been introduced to numbers throughout your grade school years. So, first off, the most basic thing you were ever introduced to was the natural numbers, right? 0, 1, 2, 3, 4, the natural numbers. And what's the first thing you learn how to do with those numbers after counting? You learn how to add them, right? And then you eventually even learn how to subtract those things. And you're able to do something like 7 take away 4. You did little problems where the teacher gave you 7 marbles, and then they took 4 marbles away from you. Said how many were left. And you could answer those questions. It was a very exciting time of life, right?
Yeah.
And then eventually you came across the problem. What about 4 minus 7? And then you said, that's broken, teacher. If you have 4 things, you can't take away 7. This doesn't work. You're cheating. Quit cheating. And the teacher said, no, no, no. There's just something out there called integers. And you were introduced to the concept of a negative number. And we call it -3. And then you became content with that, and you went on your merry little way. Now, after you learned how to add and multiply and subtract, you eventually learned how to divide. Divide things up into groups. So if I gave you 20 marbles, I said, what's 20 divided by 5? You take 20 marbles, and you split into 5 groups, and you count how many's in one group, and you see 4. 4 is in each group. And so you learn that 20 divided by 5, and you figured out that is equal to 4. Hooray! Then your teacher got tricky with you. And they said, what's 2 divided by 9? And you said, teacher, you're cheating. 9 doesn't go into 2. This doesn't work. It's somehow broken. Or what's 11 divided by 9? If you're thinking a whole, it being able to go in at least once matters. And the teacher said, it doesn't work. You're cheating. This is a bad question. It's somehow a broken problem. And you were once again introduced to a new type of number called the rationals. Introduce you to this notion of fraction. What's 11 ninths? Or what's 11 divided by 9? It's 11 ninths. And that's a perfectly good answer. And you probably thought that that was the stupidest answer you ever saw when someone first showed it to you. You didn't even solve the problem. This was the problem, and you're saying that's the answer? That's cheating. But eventually, because a lot of teachers kept telling you it, you said, fine, you can do that. And then you learned your operations, like raising things to a power. You know, 2 squared is 4, right? 3 squared is 9. And you also learned this special symbol, the square root of 9. And if I ask you what's the square root of 9, you said? 3. Wonderful. And I asked you what's the square root of 4, you said?
2.
2. And then if I ask you what's the square root of 2, you said? You're cheating. It's a bad question. It doesn't work. And hopefully, but maybe not, you're introduced to the concept of the real numbers, where the square root of 2 is, drum roll,
The square root of
the square root of 2. What? That's the problem we started with. You didn't solve anything. No, that's the answer. What's the square root of 2? It's the square root of 2. That's what it is. Taking you through some of your operations with numbers. So you got to get comfortable with, we're going to call the square root of 2 the square root of 2. And the square root of 2 is an introduction to an irrational number. An irrational number. So what's the difference between the rationals and the reals? The reals have numbers that can't be expressed as fractions. Your rationals, that's a set of all your possible fractions that you can write. Fractions of integers. The square root of 2 is not a rational number. There is no two numbers you can write, no fraction you can write that gives you the square root of 2. Another example of an irrational number you've worked a lot with is pi. But also the square root of 3, root 2 over 2, if you've done some trig, whatever. Good? So, different types of numbers. Real numbers, now we're going to be expanding the types of numbers that we talked about. Perfectly good number, square root of 2. Nothing wrong with it.
Do those groups of numbers go on forever?
Yes. So one of the ways we will think about all real numbers is all real numbers can be represented with some real part followed by an infinite number of decimal places. And you're used to using a decimal expansion to write out a number. Right? So we've got this concept of repeating decimals. See, I told you the square root of 2 can't be expressed as a decimal. Can't be expressed as a rational, a fraction. It can't be expressed as an integer over an integer. So let's talk a little bit about repeating decimals. What's a repeating decimal? It's a real number that can be expressed with a decimal part that eventually has a pattern that starts repeating. Right?
Yeah.
So all my decimal numbers, we're going to split into two categories. Either you have a decimal part that repeats some pattern, or it has a decimal part that doesn't repeat some pattern. We're going to talk about two different types of numbers here. Okay, so you're all familiar with 1/3. 1/3 represented as a decimal, that's 0.3333. When do I stop?
You don't.
You don't. It goes on forever with 3's, right? And so we have this notation for it. We say 0.3 with a bar above it, and that means repeat the 3 forever. Good?
Yep.
What about 2? Is that a repeating decimal? Does that have an infinite repeating pattern in its decimals? Yes, because 2 is the same thing as 2.0 with the 0 repeated forever. So it can be expressed as a repeating decimal. Any number that can be expressed as a repeating decimal is a repeating decimal. So 1/3 is a repeating decimal, 2 is a repeating decimal. What about 17?
Yeah.
What about 29? 119? Negative 119.
Sure.
So you see, obviously all the whole numbers are, because a repeating decimal is just 0. And so it's only fractions and other things that are more interesting. Another one like 2/3. 2/3, that's just 6 repeating forever. If you pick something like 1/11, that's going to be 0.0909090909, and it's going to have that repeating pattern. Now, if you were to do this with the square root of 2 and start writing it out, you're going to notice that there is no repeating pattern. The pattern never repeats itself, and it just keeps falling out numbers as though they're randomly being generated. Make sense? So this one cannot be expressed as a repeating decimal. The other ones can. Square root of 2 is somehow different. With me so far?
Yeah.
Okay. So let's think about repeating decimals versus rationals. How are those two related to each other? A rational is anything that can be expressed as a fraction. A repeating decimal is any number that can be expressed where the decimal repeats infinitely with some pattern. You with me?
Yeah.
So let's look at the decimal expansion of 13/11ths. Now how do we do this? What's 13 divided by 11? You've done this a million times, right? How many times does 11 go into 13? Once. So you bring down 1 times 11 is 11. Subtract it, you get the 2. You bring down your 0. How many times does 11 go into 20? Once. 1 times 11 is 11. Subtract gives us 0.9. Bring down your 0. How many times does 11 go into 0.9? 8 times. 8 times 11 is
88.
88. Subtract gives us
2.
2. Bring down the 0. And now you see, we're going to repeat exactly what we did right here.
Yeah.
How many times does 11 go into 20? It's going to go into it once. Multiply down, we're going to get a 9. Bring down the 0, 90, 8. 1, 8, 1, 8. It's going to repeat like that forever.
Yeah.
And you'll notice that any decimal you write out, eventually, it's going to spit out a number that it did earlier in the pattern. And from there, it's going to start looping and just start spitting out the same thing over and over again. And so every single rational number can be expressed as a repeating decimal. Make sense? Now, let's think about repeating decimals. Can repeating decimals be expressed as rationals?
No.
We know some of them can. For example, 2.0 repeating, can that?
Yeah.
Yeah, that's just equal to 2 over 1 if you want to think about it as a fraction. Same thing, right? So obviously that one can. What about this one? 13.179 and then 0 repeating after that.
Sure.
Can that be expressed as a fraction?
Yeah.
Very trivially. This is, let's see, how many times we have to shift the decimal place? 1, 2, 3, 4. So this is 131792 divided by 1 with 4 zeros.
Yep.
When I take this and I divide by 1 with 4 zeros, that just means shift your decimal place 4 times, and we get this number. So any decimal number that eventually has repeating zeros forever, we can obviously express as a fraction, as a rational, right? Let's try a more interesting one. Let's look at 0.9 repeating forever. You with me?
Yep.
Now not Caleb. Can this be expressed as a rational number?
No.
Let's get a sense for what this number is. So here's 0 on the real number line. Here's 1 on the real number line. We're talking about 0.9 repeating. So 0.9 is right here. Right? 0.99 is right there. 0.999 is right there. 0.9999999 is right where? Basically 1. But not quite 1, right? So 0.9 repeating, can this be expressed as some sort of fraction?
Yes, I will say.
Yeah? What's the fraction?
Will be 9 ninths, won't it?
9 ninths?
The first
Isn't that one?
No.
It's as good as the answer as any.
Oh, yeah.
9 ninths. Last year, the kid gave me 3/3. If 1/3 is 0.3 repeating forever, multiply that by 3 and you get 3/3 is 0.9 repeating forever. So, he saw it as 9 ninths. Another kid once saw it as 3/3.
They're both one.
They're both 1. Is that just equal to 1?
Not quite.
Not quite, right? There's a big difference between 0.9 and 1. But what about between 0.999999999 and 1? Well, the difference keeps getting smaller, but there's still something there. You can't just say that that equals 1, can you? Well, of course you can. And we'll see it.
They're the same.
They're the same, aren't they?
Yeah.
And we'll see how they're the same. And I'll convince you. I'll try to convince you. So let's prove that 0.9 repeating is equal to 1. How does this work? So let x equal 0.9 repeating. Good? And what does 10x equal then?
9.9 repeating.
9.9 repeating, right? Now I'm going to do some tricky algebra. I'm going to do 10x minus x. What does that give me?
9x.
9x. And I'm going to do 9.9 repeating. And I'm going to subtract 0.9 repeating. And what is that going to give me?
9.
Just 9. And those are going to be equal to each other. Divide both sides by 9. And you get x is equal to 1. So writing that out as a proof, here it is. So let x equal 0.9 repeating, and observe that 10x is equal to 9.9 repeating. Okay, then 10x minus x is the same thing as 10x minus x. Right? And then 10x minus x is 9x. 9.9 repeating minus 0.9 repeating is 9. So 9x equals 9, or 9x equals 9 times 1. In case you want to think about our algebra rules. Divide both sides by 9, and we get x is equal to 1.
Yep.
Okay, so that one worked. Is it going to be the case that every repeating decimal has a rational expression, a way of representing it as a fraction?
No, I don't.
I don't know.
Don't know. Let's try another one. Let's give ourselves some space here. We'll look at this one. 137.2164 repeating forever. There's a pretty random repeating decimal. Take you through the process here. Yes, this could be expressed as a fraction. And we're going to almost follow the exact same outline we did here. Let's see. To get this part, to get its repeating part all before the decimal, I need to multiply this by what? 10,000. Shift it 4 times, multiply it by 10,000. So we'll call that thing x for a second, and we'll figure out what x equals. First off, we have then 10,000 x is equal to 137.2164 repeating, right? And I know that x is equal to 137.2164 repeating. Right? So now, subtract them. 10,000x minus x leaves me 9,999x is equal to, subtract these from each other, and I get 1372, let's see, once 0, what's 64 minus 37?
27.
27, and then the decimal part goes away, right? So now, divide both sides by 999, and we solve for x. So x is equal to 1372027 divided by 9999. That could possibly be reduced into a simpler form. 3 probably goes into both of those, I don't know. But the point is, we were able to express as a fraction. So it turns out there's a one-to-one relationship between these two things. Every rational number has a repeating decimal expansion, and every repeating decimal expansion represents a rational number. And the ones that don't have a repeating decimal expansion are called irrational numbers. All those numbers together is what constitutes the real numbers. Real number, any number that has a decimal expansion. Good? Okay. So that was a little bit of numbers, talk about properties of numbers, then get back to measurement and the geometry stuff. Not sure if we'll need that. Maybe the scratch space. Okay, so thinking now about inequalities on the real numbers. And this is what you were just introduced to in your last algebra review. The reason the author did that was to prep you for this. So thinking about inequalities on the real numbers. We are not talking about this lesson that we were talking about on segments. Same symbol, completely different meaning. And we just repeat the same symbols. Okay, so what did we mean by x is greater than y? The definition you were given in your algebra review is that means x minus y is positive. Right? Similarly, what did it mean for x to be less than y? That meant x minus y is negative. And so inequalities have these basic properties to them. Some of which I don't know if you proved in your algebra review. Most of these proofs are pretty straightforward. So here's the properties of the inequalities. If x is greater than y and y is equal to z, then x is greater than z. Right? That one's trivial, just using the law of identity. You're done. If x is greater than y and y is greater than z, then x is greater than z. Right? How might you go about proving that? If x minus y is a positive number, and y minus z is a positive number, then x minus z is going to be a positive number. And that's the way that you would write out the proof for doing that. Okay? X is positive if and only if x is greater than 0. So if x is greater than 0, then x minus 0 is positive. And if x minus 0 is positive, then x is greater than 0. You prove both ways on those. X is negative if and only if x is less than 0. Same thing. X is greater than y if and only if x minus y is greater than 0. This just instantly follows from this. X greater than y means x minus y is positive. Here we said x is positive if and only if it's greater than 0. So x minus y is positive, therefore x minus y is greater than 0. And then reverse. And then finally, if x is greater than y and u is greater than or equal to v, then x plus u is greater than y plus v. So if x is greater than y and I add two things on either side, but the thing I add on this side is at least as big as the thing I add on this side, if not bigger, then the inequality is still going to hold after you add those numbers. Make sense? So those are the properties that those inequalities have. You could have guessed all of them, I'm guessing. But now let's get to measurement, and let's think about the actual measurement process. So I got the segment here, AB, and I want to measure it. How on earth do I measure it? What do I have to do? I give you this job, I want you to measure AB. What's the first thing you have to do?
Choose a unit.
Pick a unit. What is a unit? Think about that. What's a unit?
Anything can be a unit.
It's just some segment that exists somewhere in this universe.
Yeah.
You're just making reference to some physical segment in this universe. What is a meter?
The stick in France.
Yeah, there is some platinum rod over in France. And that is a meter. And what do we mean by a meter? We go get our sticks and we line it up with that stick and we cut it off so it's the same length, so it's congruent to it. And we walk around with those things and we say that they're meters. There's nothing special about that. Common way that they measured was a foot. You see how many feet something is. You'll line up your foot one after the other. What's the big problem there? Everyone has different feet. So what did they do? They took the king's foot, they cut off the stick the same length as it, and they said, here's a foot. And there you go. When we talk about a foot, we mean the king's foot. So as long as you're making reference to some actual segment, then, well, you need some segment to act as your metric, is my point, as your unit.
Yeah.
So you got to pick a unit, and then you can measure the length of something. What is length? It's a number together with a unit, some segment in the universe. So, if I tell you to measure AB, first thing I need to do is I need to give you a unit. Here's my unit. CD is my unit. What's its name? It's foo. Here's my unit, foo. And so the question is, how many foo is AB? Now, how do we go through this process?
You line them up.
We literally take something, cut it the same length as our foo here. I try to make it the same length as a marker. And now, once I cut off my segment the same big as foo, I come and I stick it up on here. And I say, well, if we got to here, that would be 1 foo. Here gets us to 2 foo, 3 foo, 4 foo, 5 foo. Now what? We didn't land perfectly on it. We went beyond it.
You need a smaller unit.
And now we would have to use a smaller unit. And so what unit would we want to use next? What's the most natural unit to use?
An inch.
An inch? Once I've started with foo, randomly switch to an inch? This is how we end up with 5,280 feet in a mile and 12 inches in a foot.
I just use
Half of
How about we just use a tenth of foo?
Yeah.
So we're talking about the length of AB. What's the length of AB? How many foos went into it? 1, 2, 3, 4. 4 foos went into it. But now, if we represent the length as a decimal number, our next decimal here represents how many tenths of a foo? Right?
Mm-hmm.
And so now I take 1/10 of a foo, which we'll say is about the size of, I don't know, half the lid here. And so we come up with, and we say, okay, so 1/10 of a foo got me to there, and then another tenth, oh shoot, that got me past it. And so now what should we do?
Go to
100th
100.
of a foo.
Go to 1/100th of a foo, and see how many hundredths of a foo we got. So we got 1/10 of a foo. Once we got to 2, we got to 100, or we got too far. So you keep measuring until you get one too far, then you go back to the one that was previous, and start from there, but with 1/10 of what you started with. 1/10 of whatever your unit was, the actual unit that you chose in the beginning, completely irrelevant. And if we were to repeat this process over and over again, depending on how precise we were, how accurate we were, we end up coming with some decimal expansion representing the length of that thing when we had foo here. And maybe after this, we finally landed exactly on B, and now we're done. Of course, maybe we never actually get to B. Right? Could be like the 0.9 repeating. Or is 0.99999999999 forever? And we would have to use infinite decimals to ultimately get there. That could be the case.
Yeah.
That would be the case. Give you an example of where that would actually be the case. Let's say that I gave you this square here, and it was exactly a square. Okay? And let's pretend that I constructed a square so that this side over here is exactly 1 foo. Good?
Yeah.
The question is, what's the length then of this diagonal?
Square root of 2 foo.
And it turns out it's the square root of 2 foo. Get that from the Pythagorean theorem real quick, which we'll prove later, but 1 squared plus 1 squared equals 2 squared. A squared plus b squared equals c squared. Either way, square root of 2. And square root of 2 has an infinite repeating decimal. So we would go on measuring forever. Aristotle called these two numbers incommensurate or incommensurable. They're not commeasurable numbers, is what he would say, because it has that infinite expansion. Okay? So there's the actual process of measuring something. And that's the way that we're going to think of the length of something in this class. Pick your unit, and we're going to think about it as one of these decimal expansions. Now, we didn't have to use this perfect cutting down by tens. That was completely arbitrary. I could have instead used a third of foo next. Let's remeasure this, doing it a bit differently. So first off, I come off, and it's 1, 2, 3, 4 foo, so we got that. So I could have said AB is equal to 4 foo plus, and then I could have said, next I want to use 1/19th of a foo. That's my next one. And I count how many 19ths of a foo get me there. So then it's going to be, and maybe it took me 2 to get there, so I could do plus 2/19ths. And then plus pick my next small length I want to use. And it could be in 197ths. And then it was plus 19 197ths. And it doesn't matter, since those are all rational numbers, they're all decimal numbers, you can add them all up and it's still just going to give you a decimal number. So you don't have to divide into tens, it's just the most natural thing to do. But you'll just divide it up into smaller and smaller segments as you get closer and closer to whatever that thing is. And that's the process of measuring. Right? Make sense? Okay. So now, with that, introduce you to our two postulates for this section. Postulate number 1 has a lot of words to it, but it's a pretty straightforward idea. If I were measuring the segment, AB, with my foos, I'm guaranteed that eventually I perfectly measure it and foo went into it perfectly, or I go beyond the point B, if I were to do enough foo. Right? Pick any long distance you want. Doesn't matter how long it is. Could I measure it ultimately with this marker?
Yes.
Yes, it would just be a really big number. And eventually I could get to the point where my marker goes into it perfectly, 5,286,597 times, or it goes just beyond it. You with me? That's what this postulate is going to say we can do. Okay. So let's read the postulate. Called the Archimedean postulate, or you might have come across it before as the Archimedean property. But Archimedean postulate in this class. If AB is any segment on some line L, and if CD is any other segment, CD is going to represent our unit here, then there exists some natural number. There exists, and in the natural numbers, there exists some natural number and some sequence of points, A0, A1, A2, AN minus 1, AN, such that, on L, such that CD is congruent to the distance between A0 and A1, and the distance between A0 and A1 is congruent to the distance between A1 and A2, etc. So all the segments are congruent to each other. And either the last point ends exactly on the point B, or the point B is on the last segment. Let me write this out with a picture here. So ignore that. We'll just kind of piggyback on this picture. So here's our CD, trying to understand that axiom up there. And here's our segment AB. What does that axiom say? It says that there exists some little n in the natural numbers. In our case, it's going to be 1, 2, 3, 4, 5. It's just how many times you line up your metric on here before you get beyond the point or land directly on the point. So in our case down here, little n is going to equal 5. There's going to exist some n in the natural numbers, such that if we were to take the sequence of points, this is a point A0, this is a point A1, this is a point A2, dot, dot, dot. This is the point A sub n minus 2, this is a point A sub n minus 1, and this is the point A sub n. So just lining them up. In our special case, little n is 5. So this is A sub 0, A0, same thing. I'm always going to say that. Consequence of taking physics. A0, A sub 0, A1, A2. Remember, in our special case, n here is equal to 5. So this is 5 minus 2 is 3. So A sub 3, A sub 4, A sub 5. But we could have been measuring a longer segment that went all the way to 100. That's why we're using a little n there rather than a 5. Okay, so pick any segment on L that we want and let CD be a unit. Then there exists n in the natural numbers. In our case, little n is 5. And some sequence of points, A0, A1, A2, dot, 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 A4, A5. We have those points right here. On L such that CD is congruent to A0 to A1. So CD is congruent to A0 to A1. That's how we were marking off these points. I was making sure that CD was congruent to this. They were the same length. They were 1 through, right? And A0, the segment A0, A1 is congruent to the segment A1, A2. And the segment A1, A2 is congruent to the segment A2, A3. Dot, 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 and all these segments are congruent to each other. So that's what this is saying. CD is congruent to the first segment. The first segment is congruent to the second segment. Dot, 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 and the second to last segment is congruent to the last segment. And either A sub n equals B, which would have been the case where foo perfectly went into my segment, or we have B is between A sub n minus 1 and A sub n. So we can always find a number such that we landed perfectly on B, or we just went one beyond B. And that's what the Archimedean property says. And this is our postulate. This is the one that enables us to measure things.
Why is postulate? Can you prove the Archimedean property?
You have to have some foundational property to ultimately derive it. So in real analysis, one of the ways that you come at this is with axiom that has to do with there's different ways. For the purposes of this class, it's a postulate. Okay. So that was our first new postulate for the day. You only have 2 postulates. Now this first postulate for the day essentially gave you our second big idea here. I told you our 3 big ideas. Everything has a length. We went through the process of what we mean by the length of thing. Second one was, pick a unit. Every segment has a length in terms of that unit. That's what the Archimedean property says. Pick a unit, CD, or CD here. Pick a unit, CD. Then there exists some n in the natural numbers such that CD goes into it that number of times. And the last CD, the last segment, is either going to land perfectly on your point or it's going to go just beyond your point. That's all it says. Okay, and then our last postulate here gives us our third big idea. What was our third big idea? Pick a length. There is a segment with that length. What does the completeness axiom give us? It tells us completeness axiom or completeness postulate. Sorry. In this class, completeness postulate. I'm always going to call it completeness axiom because that's what we call it in calculus, and so I'm just used to it. Okay, what does this one say? It says for any x in the real numbers, pick any real number you want. 1,297, 0.2716, repeating forever after that. Pick any real number you want. So for any x in the real numbers, for any real number, and for any point A on some line L, pick A on line L, there exists B on line L, there exists B somewhere on this line, such that the length of this segment is equal to x in terms of the units you chose. In other words, pick a unit, pick a real number. You can always construct a segment from a point that long. Right? I can always pick a point in our universe, right here, and I can now tell you to go some distance in some direction from this point. I can tell you go 2 feet that way. And you can always do that, and that gives you a segment. I could have said go 100 miles that way, and you could have done that, and that gives you a segment. That's all that this is saying.
Okay.
For any real number you can pick, we can construct a segment from some point on a line that long. Oh, I didn't tell you about this notation. So AB means the segment, AB. If we put a line above it, that means the length of the segment. So this is AB's length. This is now a number, not a segment. So AB by itself, that's a segment. That's a geometric figure. AB with this bar above it, that is now a number. Like 19, 127, or 4.1796, etc. Make sense? Just notation. Okay. So that kind of is it for the material. Just going to take you through a couple theorems now. Very unsatisfying theorems. For this first theorem, 5.1, I need to remind you of something we proved last time. So flashback to last time, one of the theorems we proved last time, what did we show? We showed that if AC is congruent to A prime C prime, so AC is congruent to A prime C prime, and B prime is between A prime and C prime, so B prime somewhere between these 2 points. And now I pick B down here. I pick B on C's side of A, so B is on C's side of A, such that AB is congruent to A prime B prime. Then I know that B must be between A and C.
Right.
Make sense?
Yes.
That's one of the things we proved last time. We'll have to use that in one of our theorems today. So now let's, we'll only be proving 2 of these. Maybe keep that review of that theorem on camera. And just don't let me go past here. Okay. So our first theorem here is now to prove that if AB is congruent to A prime B prime, then the length of AB is equal to the length of A prime B prime. Up till now, we were just using that as intuition to guide us in how we were thinking about congruence. If we got the right postulates or axioms for congruence, then this for sure better be the case. We were kind of trying to pick the postulates and axioms that would make sure that this was the case. That's like what guided us in picking those postulates, or the author. Okay, so here's what we're trying to prove. So let's get started. 1, let AB be congruent to A prime B prime. And now I need to talk about the length of AB. So how do you get the length of a segment? You're just going to have a bunch of points in between it in one length, and then you switch to a different sequence of points in a different unit, and a different sequence of points in a different unit, until ultimately you get to B, right? So I'm going to label that sequence of points. So let AB be congruent to A prime B prime, and let C1, comma, C2, comma, C3, comma, dot, 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 meaning there's potentially infinitely many of them, dot, be the sequence of points between A and B that measure AB. Whatever it is. The sequence of points that we use ultimately to determine the length of AB. Maybe just draw a picture down here really quick to help us in our thinking. So here's A. Here's B. We're going to have an A prime and a B prime. And so far, what are our points C1, C2, etc.? They're the points that we use in making the segments to measure this thing. So this could be C1, this could be C2, this could be C3, this could be, C3, this could be C4. And then at this point, we're going to have to switch whatever our unit is that we're measuring in. So C5 is going to be closer, more like that, than C6 and C7, da da da. and the points are going to keep going. Make sense? So they're the points between A and B that we use to measure the length of A and B. Good so far?
Yep.
I know that AB is congruent to A prime B prime. I'm trying to show that A prime B prime has the same length as AB. Or in other words, if you were to take, we can take a sequence of points, the same as these ones, in between A prime and B prime, and give us the same length. Make sense? So now 2. Let C1 prime, comma C2 prime, comma C3 prime, comma dot 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 be the sequence. Sequence just means we're preserving the order of the points. So C1 comes before C2, comes before C3. So let those be the sequence of points such that, and how am I going to pick C1 prime? I want to pick C1 prime so that it lines up with this point right here. So I want to pick C1 prime down here such that what is congruent to what? How do I choose C1 here if I want to match this point?
So that A prime C prime 1 is congruent to A C1.
Perfect. I need this piece to be congruent to this piece. So I need that to be congruent to that. Right? So pick these sequence of points such that A prime, C1 prime, is congruent to AC1, comma, and we're going to pick C2 prime over here so that what? How do I choose C2 prime? I want it so that this thing is congruent to this. Right? So choose C2 prime. So pick that sequence of points such that AC1 prime is congruent to that. So that C1, C2 is congruent to C1 prime, C2 prime, comma, and C2, C3 is congruent to C2, C3 prime prime, comma, dot dot dot. And do it for all the points. Put my dot 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 right here. Comma, dot dot dot. So do that for all the points. So now we've marked out all these points here. Here's C3 prime, here's C4 prime, and dot dot dot, with all these segments being congruent to their counterpart. With me so far? Okay. Now I'm trying to argue that this sequence of points then produces the length of segment A prime B prime. How will I be able to argue that? I essentially need to make sure that these sequence of points now stay completely between A prime and B prime. If these sequence of points stay completely between A and B. Because then, if they're all between them, then we can just sum up the lengths to get the points. Or sum up the lengths to get the total length, which we know equals that to equals or equals. So the only question that remains is, are all these points actually going to be between A prime and B prime? Or am I somehow secretly going to get beyond B prime? And this is where theorem 4.3 is going to come into play. Make sense? It's a bit of hand waving because we're talking about infinite things. We don't have good notation for it, and I just kind of have to give you a feel for it. These theorems are very unsatisfying. Okay, so 3. Since we know that it goes A, C1, B, and we know that A, C1, so let's see. We know that C1 is between A and B, right? I know that AB is congruent to A prime, B prime. How do I know that? How do I know AB is congruent to A prime, B prime?
We said let AB.
Right there. Let AB be congruent to A prime, B prime. That's our starting information. So obviously we have to use that somewhere. Okay, so since C1 is between A and B, since AB is congruent to A prime, B prime, comma, and AC1 is congruent to A prime, C1 prime, and A C1 is congruent to A prime C1 prime, then what? What does that give me? So I know C1's between A and B. I know AB is congruent to A prime B prime. And I know that AC1 is congruent to A prime C1 prime. So what do I know about C1 prime?
Where it's in between A prime.
It has to be between A prime and B prime. That's exactly what this says here.
Right.
What does this say here? I know that the total length is congruent to the total length. I know that this piece is congruent to this piece. And I know that this point is between these two. Therefore, this point is between these two. That's what this says. So since that, then I know that we have A prime C1 prime B prime by theorem 4.3. And then we could repeat the exact same process now using C2. So I know that C2 prime is between A prime and B prime. And C3 prime is between A prime and B prime. And that was our last thing that we needed. So similarly, for C2 prime, C3 prime, ... 5. Therefore, the two segments have the same length. You will not have any homework problems in this chapter that are proofs.
Really?
Yes. Because these proofs are so hand-wavy. So they're just going to be problems that focus more on making sure you understand these three big ideas. And that's pretty much what they're going to focus on. So you're not going to have to do proofs like this. You were probably looking at this and thinking, how on God's green earth am I going to be able to do a problem like this? It's not expected that you're supposed to. This is a very shallow proof.
Yeah.
I don't like it, but I'm giving it to you. Okay. So there you go. Let's move on now. Move the camera and then move on to our last couple theorems. I'm only going to prove one more. The other ones we're just going to make sure you understand. Does that have it all? Probably cuts off a little over there. That's fine. Okay. So now, our next theorem. Notice that this theorem gave us the implication one way. It said that if AB was congruent to A prime B prime, then they had the same length. I also want the converse to be true. I want it to be true that if they have the same length, then they're congruent. Make sense?
Yeah.
So that's going to be our second theorem here. So how does this one work? So let AB and A prime B prime be two segments. AB, A prime B prime. Here's AB, here's A prime B prime. They're two segments, and all I know about them is they have the same length. I'm trying to prove that they're congruent. Make sense? Okay, so let AB have the same length as A prime B prime. And now we're going to pick B double prime such that A prime B double prime is congruent to AB. And B double prime could be over here. B double prime could land exactly on B prime, which we know it does. Or B double prime could be over here. Has to be one of those three cases. I'm going to show it's impossible for B double prime to be over here, and it's impossible for B double prime to be over here, therefore it has to be on B prime. And so the two segments are congruent to each other. So, let AB have the same length as A prime B prime, and let B double prime be the point on B prime's side of A prime. So pick a point over here on B prime side of A prime. So here's A prime, go to this side, and we're going to pick the point B double prime wherever it lands. That makes this segment congruent to this segment. We know the point lands here. Showing it here, impossible picture. We're going to show it's impossible for it to be there or there. So, let B double prime on B prime's side of A prime, such that AB is congruent to A prime B double prime. Now, assume by way of contradiction that B prime, or that B double prime is not B prime. That it doesn't land exactly on there. Impossible. We're going to show it's impossible. So assume by way of contradiction that B double prime is not B prime. And if B double prime does not land on B prime, then we either get A prime B double prime B prime, or we get A prime B double prime. Has to be one of those two cases. And so if it's not exactly on the point, then we either have B prime is between A prime and B double prime, or we have B double prime is between A prime and B prime. Has to be one of those two. Let me show that both those are impossible, therefore it had to land directly on it. Okay? Now, so looking at our impossible picture, so B double prime landing over here or over here, I'm going to call the length of this segment, B prime, B double prime, I'm going to call its length little a. And so little a can signify that length or it can signify that length. Same length in either case, right? Because same segment. Okay. So let A, be the length of B prime, B double prime. So A is a number. And observe that if A is 0, what happens if the distance between B prime and B double prime is 0?
They're the same.
Then they're the same point, right? And so, observe that if A equaling 0 tells us the same thing as B prime is equal to B double prime. I'm going to show that in both these cases, A is equal to 0, which is impossible. Therefore, both those cases are impossible. Right? So we're going to start the first case. So we're assuming that B prime and B double prime are two separate points. And let's see which way we go first. Oh, sorry, let's make our note here. No. Note that if AB is congruent to A prime B double prime, then AB has the same length as A prime B double prime. How do I know that? How do I know that if two segments are congruent, then they have the same length? Isn't that what I'm trying to prove?
No.
What am I trying to prove?
Trying to prove that they have the same length and they are congruent.
I'm trying to show if they have the same length, then they're congruent. I'm saying note that since AB is congruent to A prime B double prime, then they have the same length. How do I know that? Our previous theorem. Our previous theorem says if they're congruent, then they have the same length. Now we're trying to show if they have the same length, then they're congruent. So I can use the fact that if they're congruent, then they have the same length. I already know I chose B double prime. I chose B double prime so that A prime B double prime is congruent to AB. That was my choice of B double prime.
Yeah.
So I know that AB is congruent to A prime B double prime, which means that they must have the same length. And so there's going to be two lengths being equal here that we're going to use to get our contradictions. So I know the length of AB is equal to the length of A prime B prime, and I know that the length of AB is equal to the length of A prime B double prime. The only way that's possible is if A prime and B prime, or if B prime and B double prime are the same point, which we're showing. So we're going to show that it's impossible for them to not be the same point. All right, so let's show the impossible now. So if B prime is between A prime and B double prime, so we're handling this case where A is right here. So ignore that point. We have A prime, B double prime. Doing that case first. So if B prime is between A prime and B double prime, it looks like this, then what is the length, so ignore B double prime here for a second, what is the length of A prime B double prime? It's going to be the length of this segment plus this segment. You with me? So the length of A prime B double prime is equal to the length of A prime B prime plus the length of B prime B double prime. Good? Now the length of B prime B double prime, that's just a number. We're going to call that number A. We already said that we're going to call A that length somewhere up here. Right here. So that is just A. So that distance then is equal to B prime to B double prime, that's just A. But now I know that the length of A prime B prime is the same thing as the length of AB. So I'm substituting this with this. Here's one substitution. How do I justify that? This. And then my other substitution, that's substituting this and this. And then replacing that with A. This substitution comes right here. So the length of A prime B double prime is equal to the length of AB. The length of A prime B prime is equal to the length of AB. And then the length of B prime B double prime is equal to little a. You with me? And so I got something equals that something plus A.
So A 0.
Yeah, subtract something now from both sides and I get A equals 0. A equals 0 means that B prime is equal to B double prime. Contradiction. How's that contradiction? We said B double prime is different from B prime. We got B double prime is the same as B prime.
Right.
Make sense?
Yep.
Now we repeat. So we showed that this case is impossible. Now we need to show that this case is impossible. B double prime being right here. So erase that. And now we're looking at the case where B double prime is right there, and we're going to show once again that this is an impossible picture. So now if B double prime is between A prime and B prime, like that, then what do we get? We get the length of A prime B prime is equal to the length of A prime B double prime plus the length of B prime B double prime. Good? Now, using our substitutions again, the length of A prime B prime is the same thing as the length of AB. So replace that with that. The length of A prime B double prime is the same thing as the length of AB. And the length of B double prime to B is A. So I get the same thing is equal to the same thing plus A, which means A is 0, which means the points are the same. Contradiction. So B double prime couldn't be on this side of B prime, and B double prime couldn't be on this side of B prime. So B double prime has to land exactly on B prime. And so the two segments are congruent. So therefore B prime is equal to B double prime, and so AB is congruent to A prime B prime. Make sense? Cool. Two more theorems, neither of which we're going to prove. We're just going to tell you in words so you get the idea. It's right here. Theorem 5.3, very similar. If the segment AB is greater than the segment CD, this is using the segment notion of greater than, that's what we reviewed at the start of class, then the length of segment AB is greater than the length of segment CD. And vice versa. So that's an if and only if. So if I know this is true, then I know this is true, and if I know this is true, then I know this is true. This again has a wordy proof with sequences like this. It's not worth it. But make sure you understand the idea. Pretty straightforward idea. We've already guessed that. And then finally, our last theorem is our most interesting one. And one that, again, is very intuitive. How does this one work? I tell you that AB is 7 feet long. And I tell you that 1 foot is 12 inches long. How long is AB in terms of inches? 12 times 7. So it's 12 times 7 inches, or in other words, it's 84 inches long. Right? So now here's what it says. Maybe, well, no, that could help. Here's AB, here's CD, here's EF. And here's our table measuring AB. Well, we'll just see if I got this one. Okay, so I've got the segment AB, and suppose I tell you that the length of this segment is X. The length of the segment is X when CD is the unit.
Okay.
And I tell you that the length of CD is Y when EF is the unit. Question, what is the length of AB when EF is the unit? Let's go back to a concrete case. Let's say that this, going to lie with my picture a little bit, let's say that this was 3 CDs.
Okay.
And let's say that CD was 2 EFs. Question, how big was AB in terms of EFs? 6. If AB is X CDs and CD is Y EFs, how many EFs is AB? It's just X times Y EFs, right? So if we're talking about our length of AB here and we put our units here, so AB is X when we're using CD as our units, and it's Y, then it's going to be X times Y when we're using EF as our units. Right? And you do this all the time. It's exactly the thinking you did here. AB is 7 when foot is our unit, and a foot is 12 when inch is our unit. What is AB when inches are unit? 7 times 12. Same thinking. So you're already used to this. It's just converting between units. Make sense? That's it. That's the end of the chapter. This is going to be your easiest chapter homework-wise. Any questions on any of the material? Fantastic. You have the rest of class for homework, I guess.
Take a break.
Yeah, you can take a break.